we are given a sorted array of integers and a target value. Our goal is to return the index of a target if it exists, or -1 otherwise. The constraint is strict. We must achieve O log n runtime complexity. This rules out linear scanning and demands a divide-and-conquer strategy. The naive approach checks every element from start to finish. This takes O(n) time, because we might inspect the entire array before finding the target or confirming it is absent. Since the array is sorted, this ignores valuable structural information about the order of elements. The reusable pattern here is binary search on a sorted range. It relies on maintaining 2 pointers, typically called left and right, which define the current search window. At each step, we look at the middle element and decide whether to discard the left or right half based on comparison with the target. Let us trace this with the example array -1, 0, 3, 5, 9, 12 and target 9. Initially, left is 0 and right is 5. The middle index is 2, pointing to value 3. Since 3 is less than 9, we discard the left half by moving left to 3. Now the window is indices 3 through 5. The new middle is 4, pointing to value 9. This matches our target exactly, so we return index 4 immediately. We initialize 2 integer variables for the search boundaries. We set left to 0 and right to the last index of the array. This establishes the full range of potential candidates before we begin any comparisons. Inside the loop, we calculate the middle index by adding left and right and dividing by 2. This gives us the pivot point around which we will split our current search window in half. We compare the value at the middle index with our target integer. This comparison is the core decision-making step that determines which half of the array contains the answer. If the middle value equals the target, we have found our element and return the middle index immediately. This short-circuits the loop, because no further searching is necessary once the exact match is located. If the middle value is less than the target must be in the right half. We update left to be 1 greater than the middle index to exclude the current middle and everything to its left. Conversely, if the middle value is greater than the target must be in the left half. We update right to be 1 less than the middle index to exclude the current middle and everything to its right. The loop continues while left is less than or equal to right. This condition ensures we have at least 1 element remaining to check before terminating the search process. An interviewer might ask about finding the first or last occurrence of a duplicate target. This requires modifying the boundary updates to continue searching even after a match is found. They might also ask about rotated sorted arrays, which adds a conditional check to determine which half is properly sorted. The brute force approach runs in O(n) time by checking every element. Binary search reduces this to O log n time, because we have the search space at each step. The space complexity remains O(1) since we only use a few integer variables for pointers. Binary search is the definitive pattern for efficient lookup in sorted data. Mastering the boundary updates and loop conditions will save you from off-by-one errors. Go implement this pattern on your own to solidify your understanding of logarithmic time complexity.